what you're seeing right here is a device I call the ARC1, codenamed the ARC Reboot. As you can see things loading into view, those redstone things, that's our simulation distance, which poses a major um, struggle with this device. But this thing, this whole thing here, the unit, the ARC1, this thing is a year in the making. This one specifically, at least, is 6 months. This world specifically is about 4 months. Where, of course, 4 of those months were spent having given up on the project since of an issue I'll talk about later. But this device, um, if we come down here, I'm just gonna emphasize the speed real quick because it works at the speed. Um, we're looking at 11, well, actually 12 repeaters, and they're all on max tick, which is 4, so 12 times 4 is whatever 12 times 4 is, about 48. 48 ticks is about almost 5 seconds, it's about 5 seconds, it's close enough. 5 second hertz, I don't know when to do all the math here, but it's pretty decent fast, but the only thing is that it's not executing at that speed, it's looping at that speed. So this CPU is called the ARC1, and the reason why it is called the ARC1 is because ARC stands for Advanced Redstone Computer, and I'm calling it advanced because it is greatly inspired by how real-world computers work. And real-world computers work by receiving data from RAM and then executing based off of that data. Um, the RAM stores the code. Now, normal Redstone CPUs these days, they run with ROM. And to tell what ROM is, there's RAM and there's ROM. RAM, which is random access memory, which is what I have in this device, and then ROM, which is read-only memory. They have two different functions, but they basically serve the same goal as what the program is in mind, which is holding data for the CPU to execute. If you see in here, we have data stored in RAM, and this CPU runs off of RAM to execute its code. So this is a RAM-based CPU. However, that poses its complications. Our RAM is 8-bit, just like the whole CPU, and that means we can't store a large amount of data in those 8 bits, only 256 states. So I'm doing a method that regular Redstone computers do, not Redstone computers, but real computers, and that's using something called Opcode, which is operation code for computers. Opcode is a hexadecimal value, which the CPU decodes and then executes on. This CPU is a 4-cycle CPU, which takes 3 different, one opcode and 2 operands, and then executes on that data. It could be slimmed down, but for the sake of functionality, this thing has 3, which means every cycle you're taking, like every clock, which is that 5-second clock, takes 1 byte of RAM and finds its way into the CPU and then stores it. I'll show the CPU more in depth later. This RAM is, as you can see, very inefficient. I'm playing in Bedrock, which comes with its limitations. So I have to use these quite big redstone cells, my memory cells. But I did this, which is so wide and slow, but the advantage of it is it's thin, meaning I can stack it every 2 tiles, which allows me to store 64 bytes, that's how big this is, in only 128 blocks, which is actually very good. It fits nice and tidy inside of our 10 chunk simulation distance, and it works. The main issues, like I said, is it's the speed. The further out you go, the longer it takes for the bits to travel across the whole CPU. But if we get an aerial view, it kind of looks pretty good. I think it came out pretty well. Aerial view is a little hard to get, but you'll see this, whereas I can't because my little Twitch symbol there. How did I do that? That's lifted? I actually don't remember exactly how I did this. But yeah, over here it's the same deal. The 8-bit CPU, it's a 5 clock tick, which is, I don't know, probably about a 0.2 hertz, because of 1/5. So, let's get into the mean beans of the CPU. The way this CPU works. Here's our input. This is the universal input for the serial, not serial, binary bus, and it comes into this bus right here. It ends right here, not far at all. However, it does go vertically as well, which is where its values will go, its numbers. And if we look right here, we have the end to that bus and the end of another bus, which goes through the top. So this bus goes two places, up and straight is where a lot of the use of the CPU goes into. You can't see it easily, but there are torches. I guess they're on the other side, over here, and these torches go in like on these paths. This one right here, going into these two registers. Ignore this value; it's not gonna matter anyway. These are two registers, really close to each other, separated by this, which is the read lines, and the write lines as well. These two registers are the register A and the register B, respectively. And over here is what I call the system well, these are all system registers, but I often refer to this as the system register because it is the one that stores the system command, which is the one that it'll execute. This is where our operand is stored, which is the very first byte taken from RAM. I have a few manual overrides, like a manual read, or manual write, and then manual read, which is used for like tracking and whatnot, but I haven't checked every single operand or opcode, but I'm pretty sure that most of them work. I've only tested the ones that really mattered toward my code, because I didn't really need to test a lot more. As long as it works with this, everything else can be decoded and worked out, and everything I've tested, it works. So those are the system registers. The CPU has 8 bytes of cache, which we can see right here, which uses the same memory cell, but with a little bit of a unique design. This memory cell requires a unique writing mechanism, and I actually got this from a fellow YouTuber, which I don't need to shout him out, but I will. Darth Dub on YouTube. He creates Redstone videos, and he is the one who set me on this path. He created a video showcasing an old RAM design that I have. Maybe if I show off my original world, I'll show it off, but his memory cell I used as inspiration, not for this design, but for a very old design. It was very big. It was definitely thinner than this. It was only like 3 blocks per bit, but it was 4 blocks long. So you get half as many bytes in the end. So I fixed that in this model, but the RAM at all existing just inspired me to design this. Oh crap, I have to do this manually. The main problems is that I don't have an automatic reset for the cache, and as you can see, how many block updates there are, because each of these write lines has 3 blocks, and then there's 8 of them, so writing a single line takes a bit long, but it does not affect the overall performance of the world. But there was a video, I forget who made it, but if you look up Minecraft Redstone RAM or whatever, where you can get this dual read RAM design, but I used it for my cache. It's a dual read design. I don't have the original build over there, so I can't easily show it in depth, but I used its dual read design and then added my Bedrock memory cell, so that I used a Java RAM design for a Bedrock RAM setup, even though it was not compatible. I think I get it. I should stop copying myself or repeating myself. So anyway, dual read RAM, dual read cache specifically for this. That's the function it's used for, is to store close read data, which in the end, if I'm honest, doesn't matter anyway, since, well, RAM's right here and it's always taking from RAM, but it does help with making sure everything works, because it would take a lot longer for the data from RAM to get up to the top, because if we look at our ALU, it follows, I think, Noob Master or Swift 16, one of them, not Noob Master. Um, there is a video on this ALU design. I'll probably link it in the description. Same with the dual read RAM in case you guys have Bedrock. Java. But this is an ALU, which is used for. It's a 12-function ALU, but only a few functions are used in my opcode, but I hooked everything up anyway. So the ALU is connected to both outputs of the cache, but also the B output of the cache heads out in the very end of the CPU too. It's a kind of like dual purpose, or actually tri-purpose, because if we come to this red here, it's a comparator. This comparator is used for comparison-based logic, such as greater than, less than, or equal to. Right now it's equal to because they're both 0. It was just as simple as hooking up another XOR gate and creating a decoder based on whether or not this pulse gets to the end here with or without this pulse. I forget the exact details of it, but it basically allows me to easily tell which one is which. This will always be on, but it'll only write to this register, which stores the output. As you can see, it's storing a less than or a greater than. I forget which one, but it works. It's been a while since I've worked on this part of the computer. So yeah, it'll only write to it when you want it to, and you'll only read from it when you want it to. So if you were to ever code for this computer, you got to make sure to write it and then read it, so that you don't get last cycles, whatever, whatnot. I'm not good at talking, am I? Yeah, let's show off the CPU states. The CPU has 4 states: a state 1, state 2, state 3, and state 4. First 3 states are just the gathering of data, and then the 4th state is the execution of said data. It's very inefficient, I will say. It takes 15 seconds because it's 5 hertz, or no, 0.2 hertz, times 3. So after that 4th one is when it executes. So it's about 20 seconds per command, 5 seconds per cycle, CPU cycle. So yeah, this data, it stores the CPU state, which is used to tell the CPU what it's doing. The first 3 cycles will manually gather from RAM, and then save it to the intended registers. It keeps track of its location in the program here, in the address register. Yes, I think that's it. This address register is a semi-unique design, which simply just sends a pulse forward and will always increment by 1 unless you use a goto, which powers on a few other parts of it, and then you can save any value into the register and it will always increment from there accurately. You use this for gotos. You can goto always or goto in a specific condition, and you don't even always have to display it. Only display it, the output, the contents of your counter whenever you're needing it, like in the 3 CPU states where it gathers data from RAM for execution. The B input from cache also comes out directly here, and they both can come out here, just wraps all the way to the front of the RAM. The address bus goes straight into the decoders, which gotta say the decoders are the reason why I quit this project a while ago, and I'll get back into that in a second. The data bus, the main bus, goes to the display screen and into RAM. The display screen is just a simple register. I just made this thing in like a few minutes. It wasn't really special. It was just designed to store value instead of having to display it manually, so that the computer could just send a pulse here. It would write the value from the bus onto the register, and then it would display until it was until it tells it not to. But the only time it tells it not to is when the CPU is turned off. I didn't really add a lot of functionality to this thing, did I? So after that, there's not a whole lot left beyond testing it. I am going to explain why this project took me so long. So if we take a look at this decoder, um, I kind of designed it after these 16 bytes, 16 byte sections. So every 16 bytes, it's exactly the same except for these 2 bits. Um, that way I could avoid coding all of those, and I could only focus on the ones that were changing after 16 bytes. And so I built all of this, I copied it, and then I tried to paste it right here. I didn't paste it right here. I pasted it in there and overrode like all of this. You can see why I was a little mad. Um, I was done with the computer at that point. There was not a whole lot left to do. I've done a lot since I came back to the project, so there was a lot more to do than I would have known. But it was very discouraging, so I quit the project. And after I moved out, here I am. I have a lot of free time on my hands when I'm at home, and I can record and speak without issue, so without disrupting anybody, so I do that. The CPU works. I put it together. I fixed the inside of the CPU. Finished the decoder completely. Hooked it up to the CPU. Hooked everything up. Fixed a little issue because the decoder's backwards, so your opcode has to be backwards, whereas the inside bits are the least significant bits, and out here are the most significant bits. It has to be the other way around for the opcode. But other than that, it works just fine. And technically, and I'm gonna be honest right here, it is possible to execute data, not execute, to write a program that allows you to create data, create program while the computer is running. It's not easy. You have to write it first, but it's not really easy at all. Once you write it, it's gonna be slow, but it will work. But you can write a program into here while your program's running, and then run it. It just takes a simple loop. You can do a conditional loop and whatnot. That does bring us to our major flaw of this computer, other than its speed, its lack thereof of speed. The input right here has an option right here. This thing will tell the computer when you want to send your input from here. Your input into the computer, it will receive it only when this is on. The problem with that, with this design, is there is no halting. The computer cannot halt. I completely forgot to add it. I mean, I know now how to add it, but I'm so unfamiliar with this part of the computer right now that I don't even try. I mean, all of this is baseless because I tried to add a speed. Like, you can select different speed to run the computer at, but it basically became pointless, so I kind of just unhooked everything. But other than that, this is done. Now I'm going to run the Fibonacci sequence. I don't have a recording of the new speed with the Fibonacci sequence, but it is a lot faster than it was before. It's 1 minute per loop, plus 15 seconds for the first command, which is just starting off the Fibonacci sequence. It is a 5 command, no, it is a 6 command loop. It loops 5 different commands, one of them being mathematical, arithmetic, whatnot, and the others being rearranging data in the cache for the next loop, and then it displays the data on screen, and then it loops back to the beginning. Not the very beginning where it has to preset the data, but the beginning of the loop, because conditional jumps is very easy to do in this design. So, without further ado, the Fibonacci sequence does not require an input, so I don't have to worry about timing or anything like that. Oh, by the way, let me add, it is possible to write a program with waiting in mind for your inputs. You can just create a program. It takes about it takes 2 commands, 6 loops for you just check if your input, the cache storing your input, check if it's 0. And if it's 0, just loop back to where the input is. The issue is obviously that it takes a god awful amount of time just to do this, but it is a way to work around the flaw. But in the next model, this thing's gonna have so many revisions. You're talking about a BCD decoder for the screen. You're talking about a lot of functions that are going to be added now that I have experience building a working computer. But instead of just saying it's a working computer, let's showcase the working computer. Starting the Fibonacci sequence. Down here is where I keep track of the code. I should probably put, the redstone lamps so that I can see more easily. Probably put it like down here or something. That's what I should do. But, we are taking a look at the Fibonacci sequence. And if you don't know what the Fibonacci sequence is, while we're waiting for it to really start up, the Fibonacci sequence is a mathematical sequence of numbers that adds the two previous numbers to get your output. And this basically proves the functionality of a computer. It is the all testament of a Redstone computer, and every single Minecraft build I've ever seen with a Redstone computer has tested and run the Fibonacci sequence. I've written mine in 6 lines of code, which equals out to, I forgot how many, 24 bytes of memory, which is almost half of, it's a bit less than half of this entire computer's memory. But other than that, it's a pretty simplified code. I did write this code specifically all by myself, considering the fact that the opcode that I use is what I call the ZAC language, which stands for Zypher's Arithmetic Control Code opcode. I'm gonna retire that like immediately because of all the flaws in it. So yeah, that's why I'm probably not gonna release this design. So in any case, we're about to display the first number on screen right now, actually, and we're at 1. I'm gonna get off the mic, and we're gonna let this play through. I'm probably gonna play through to the very end of the Fibonacci sequence, so yeah, enjoy. I will speed this up, most likely, in the editing, so you won't have to sit so long. I'll put music, too. That'll be fun.